We are now recording. Let me get from current slide and just cover a couple of things. I think I've announced these before. I know you're the only Lawson student, right? Are you a Lawson student? Okay. You're two. Okay. You know about the math team and math club. You know that's meeting Tuesday afternoons, 4:30 to 5:30 on the Birmingham West Campus, C100. Mr. Rossi is the coach and leading that. And then this other thing, STEM Jobs, releases a new tool to connect classrooms to careers. It's called the STEM Type Navigator, or STEM standing for Science, Technology, Engineering, and Math. So, it connects people with their interests, hopefully to encourage them to stay in the STEM field. All right. Any questions on anything we've done up till now? Okay. What we were talking about before, we started chapter 9 last time, which is infinite series. But before you do series, you do sequences. So we're in 9.1, which is sequences. And right at the end of the period, we talked about the squeeze theorem. Remember how that goes? I got a sneeze, sorry. Okay. If you have one sequence that has a limit as your n is going to some value, n is going to infinity, and you have another sequence that is going to the same value, and you have yet a third sequence that's in between the other sequences, it's got to go to the same value. Okay. And the color, right? Okay. So that's what we're going to use here. Show that the sequence, and here's the sequence C sub n, which is -1 raised to the n over n factorial, converges and find its limit. And this is, gotta find you. Why can't I find you? Davis, right? Right by you. I couldn't read my writing. I was thinking it said Davis, David, and I was looking for Davis. So now I found it. Okay. All right. We're asked to show that this sequence, C sub n, which is -1 raised to the n power times 1 over n factorial, converges and find its limit. Okay? Now, would it be helpful to list a few terms in the sequence? What you think? Okay, why not? So let's list, let me get my pen set up. You don't have to do this, but sometimes it's helpful to get an idea of what's going on. For some reason I can't get the purple. There it goes. Okay. So C sub 1 would be what? -1. C sub 2 would be 1/2. C sub 3 would be -1 over 6. C sub 4 would be (1 over 24). Okay? Let me just give you a simple way to do this, sort of simple. Obviously, signs alternating every time, so this would be a minus. Odd terms in the sequence are going to be negative, even are going to be odd, or positive. Okay, and just multiply the 5 times the 24. Okay, the suffix here by the previous, and that would be 1 over, what's that, 120? Next one, C6, would be positive 1 over 6 times that would be 720, right? Okay. Now, it says show that it converges. I think it's pretty clear it's got to be converging, right? Okay. And what do you think it's converging to? What's this limit? 0, yeah. They're getting smaller and smaller fractions big time, okay? So certainly that's going to 0, okay? Now, I have a feeling that's not what they had in mind, okay? I think they want us to use the squeeze theorem to do it, because that's what it says, using the squeeze theorem. Well, here's what my guess is on it. Let's look at 2 other sequences. Let's first look at A sub n, which let's call, is that usually the one that's the lower? Yeah. Okay. Let that be negative 1 over n prime, right? And B sub n is equal to 1 over n factorial. Okay, I said n prime, I meant n factorial. Okay? Now, you tell me, isn't every term in A sub n less than or equal to that one? Yes. And this one's less than or equal to this one, right? Because these are all positive, these are all negative. These alternate back and forth between positive and negative. So this one's in between those two, right? Okay. This converges, that converges, and converges. So therefore, the one in between converges also. You see how that works? Okay? You didn't have to list those things, but just to give you an idea of what they were. Okay? Now, I don't know, that's probably not the way they want to do it, but it seems like to me that it works. Okay? Now, maybe we haven't proven that 1 over n factorial converges, but my word, look at it. It's got to be converging. But they're going to do it slightly differently, so let's take a look at how they do it. Okay? And this is good too. To apply the squeeze theorem, you must find 2 convergent sequences that can be related to c to the n. Okay? I did, but they don't like them, I don't think. Here's the possibility. A sub n is negative 1/2 to the n, and B sub n is positive 1/2 to the n. Okay? I use negative 1 over n factorial and positive 1 over n factorial. They both work, but this certainly does too. Okay? And both of those converge to 0. That's the thing. I know we had done this, that converges to 0. We may not have done the others. That's the only fly in that one. Okay? And that's probably why they didn't want to do that. Okay? But negative 1/2 to the nth power, negative 1 over 2 to the nth power. I'll phrase it that way. That's always negative, but going towards 0. 1 over 2 to the nth is always positive, going to 0. And obviously, this 1, or I say obviously, I think we showed earlier in the, no we didn't. Oh yeah. Let's just see how they continue here. By comparing the n factorial term with the 2 to the nth term, so let's do this. Here's n factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 all the way up to n. Okay? And 2 to the nth is 2 times 2 times 2 times 2 times 2 times 2 times 2. Okay? Now, down here, 1 over 2 to the n is less than 1 over n factorial for this one and that one, okay? But starting, and even this one, okay? But starting right here, this is, in fact, 1 over n factorial is now less than this, because n factorial is greater than 2 to the n. This is 2 times 2 times 2 times 2, that's 16. This is 2 times 3 times 4, which is 24. So 1 over 16 is actually greater than 1 over 24. So once you get past that point, this keeps getting smaller very much faster than this does, okay? Once you get past 24 and 16, it's obvious that the factorial here is getting bigger. This is staying basically getting bigger, but not nearly as fast as factorial, okay? So therefore, the inverse of that would be quite a bit less. So anything past n equal 4, and you've got factors that are definitely 1 over n factorial will be less than 1 over 2 to the n, okay? Now you can do the same from the negative side, and you see the first few terms are outside, okay? Then after a while they are inside and stay inside. So if these both are going to 0, then the 1 over n factorial has to be going to 0. For sure, certain, without any doubt at all. Okay? Actually, I don't know why you couldn't have done positive 1 over n factorial, negative 1 over n factorial. It's been a lot easier to show. But fine, they still work. Okay. So by the squeeze theorem, it follows that the limit of the one in between the two has to be going to 0 as well. Now, that leads, on the next page, to the absolute value theorem. Okay? And here's what that one says. For a sequence, a sub n, if the limit of the absolute value of a sub n, which means the a sub n's are always going to be positive. Well, if that series is 0, then if the a sub n can be varying, positive and negative, don't have to always be positive, then for sure those are going to have to do. So let's just take, for instance, what if the a sub n is always positive anyway, because this thing is the same as that thing? So that would be 0, obviously. Okay? If a sub n is sometimes positive and sometimes negative, then the absolute value is going to be greater than the negative value for sure. So that's going to, if this is going to 0, then that also would have to be going to 0. So if they're moving up and down as opposed to like this, if this is going to 0, then the up and down has got to be going to 0 as well. Okay? And I think the squeeze theorem will be used to prove that if they show it, and they don't. Yes, they do show that. Not on the slide, but on the little proof at the end. Pretty, hopefully obvious. Okay? Let me just go back to this and show it. The limit is a sub n, absolute value of a sub n, that's what they're giving us, that's equal to 0. And what they do is then the limit as n approaches infinity of negative absolute value a sub n is also going to be 0. Okay, because if the positive limit is going to 0, the negative of that limit is also going to 0. I mean, have no choice. And then the limit is a sub n. It's either going to be positive, or it's going to be negative, or it's going to be alternating. It's got to be between the other two. This one will always be less than that. That will always be less than or equal to that. So squeeze theorem shows that has to be the case. All right. Now, pattern recognition for sequences. Okay? Sometimes the terms of a sequence are generated by some rule that does not explicitly identify the nth term of the sequence. If you have such a case, you may be required to discover a pattern in the sequence and to describe the nth term. Okay? If it doesn't explicitly identify it, you may have to find the pattern. Once the nth term has been specified, you can investigate whether that converges or diverges. Okay? Whether the sequence does. Okay? Here's example 6. Find a sequence A sub n whose first 5 terms are this: 2 over 1, 4 over 3, 8 over 5, 16 over 7, 32 over 9. Okay? Then determine whether the sequence you have chosen converges or diverges. So you tell me, can you see a pattern here? What?
Exponents are raising of 2 n plus 1. 2 raised to n plus 1 on the bottom is just plus 2.
1 on the bottom is what?
Plus 2.
Okay, right, okay. In other words, odd integers on the bottom and powers of 2 on the top. Okay? So find the sequence whose first 5 terms are that. So I would say A sub n, if you want to call it A, you can name it anything you want to. And this would be 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. So that would be 2 to the nth, right? The nth term would be that. And then the denominator is, okay, let's try 2n minus 1. Okay? 2 times 1 minus 1 would be 1. 2 times 2 minus 1 would be 3. 2 times 3 minus 1 would be 5. So that would be 2n minus 1. Right? Now, there is our sequence. The nth term in the sequence. Okay? Then determine whether that sequence we have chosen converges or diverges. What do you think?
Diverges.
Looks like it's got to be diverging. This is 2, 1.3, 1.6, 2 point something, okay, 3 point something, 4 point, yeah. The 2 to the n is increasing much faster than the denominator. First few, no, but after a few terms, for sure. The numerator is taking off much bigger than the denominator, so this is a diverging sequence. Okay? Now, first, note that the numerators are successive powers of 2. The denominators form the sequence of positive odd integers. By comparing a sub n with n, you have the following pattern: 2 to the n over 2n minus 1. Okay? Now, it says consider the function of real variable. Okay, I hadn't thought of doing this, but you could do it. F of x is 2 to the x over 2x minus 1. Well, we want the limit of that function as x is approaching infinity. Well, let's do L'Hopital's rule. Okay? And do y'all remember that is the derivative of this? It's 2 to the x times log 2. That's not something I usually memorize. And I know we had one sort of similar to this last time. It was right at the end of the class, so I didn't take the time to show how you get that. You want to see how you get that? Or you could just, if that's something you remember, good, fine, go for it. But here's what I do. Let's say y is equal to 2 to the x, okay? Let's not one that I'm particularly comfortable in taking the derivative for. So let's do dy. Well, no, let's start this way. What we want to do ultimately is get dy dx, right? The derivative of that. So here's how I'm going to proceed. Let's do an e of both sides. That would be e to the y is equal to e to the 2 to the x, right? By that? Okay. This will then be e to the y is equal to sorry, I did the wrong way. Let's do log, not e's. Okay, sorry. Let's take the log of both sides. Sorry, that's the one we want. Log y is equal to log 2 to the x. That's better. This will be log y is equal to x times log 2. Right? Now take the derivative of both sides. Right? Derivative of log y would be 1 over y prime, right? Chain rule. Got it? Is equal to log 2. Now, all you do is multiply both sides by y. Okay? So that gives you dy dx is equal to y, which is 2 to the x times log 2. And that, sure enough, is what we've got there. The derivative of that is 2 to the x log 2. All right. Now, derivative of the denominator is just 2. Now let that go, x go to infinity here. This is going to infinity big time, really fast. This is going to 2. So obviously that is going to infinity. That does not converge. This is a divergent series. Sequence. Any questions on that? Okay. Let me clear my writing out of the way in case they put another line here. I don't know if they do. Yes, they do. Next, apply theorem 9.1 to conclude. If you take the derivative of the numerator and denominator, it's going to infinity. So the limit of the function is the same as the limit as the quotient of the derivatives of those functions, which is infinity. All right. So the sequence diverges. That was example 6. Okay? I think now we do example 7. I don't know why they skipped a bunch of stuff here, but let's go back and do example 7. Okay? All right. Here's example 7. Determine the nth term for a sequence whose first 5 terms are this: negative 2 over 1, 8 over 2, negative 26 over 6, is that right? Yeah. 80 over 24, negative 242 over 120. Anything come to mind? Anything at all? Any observation? Okay. Now, if nothing else, if someone has a calculator, let's just plug in some numbers. Okay? You don't need a calculator for this. This will be negative 2. That'll be 4. This will be negative 4 point something. What would that be? 80 divided by 24. Second? 3 point something. How about negative 242 over 120? negative 2 point something, right? So even though they started getting bigger, they start getting smaller now. So I'm not sure that what this might not converge. At first glance, I would have said no way, okay? But I'm not as sure now. Now, anything pop into your head as you look at this?
The bottom.
What about the bottom?
The bottom doubles, then triples, then quadruples, then just
Okay. Okay. Except the next one didn't fight. Well, actually it did. Okay. Actually, what you just described is the denominator is n factorial. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and 4 factorial. Because you exactly what you said, you multiply them right. Okay. So I have at least part of a pattern here. The a sub n term is going to be something, I'm sorry, let me not put a 1 there, something over n factorial. Okay. Now the issue, got something else here. This is minus 1 to the nth power because it's alternating signs. So that's okay. That accounts for the sign change. Now, if we could only figure out what's going on in the numerator. One thing I noticed is they're all divisible by 2, right? So let's pull out a 2. Now let's see what we got once we pulled out a 2. The denominator and the minus sign. It's 1, 4, 13, 40, 121. That didn't help much, did it? Okay. All right. Yeah. Man. I did write it right, didn't I? Okay, what else could be in that pattern?
If you multiply times 3 each, I think.
Say that again?
Multiply times 3 and then add or subtract 2, right?
Multiply by 3 and add 1?
Add 2.
Add 2. If you multiply 1 by 3 and add 1, you get 4.
I'm talking about like on the original one.
Oh, okay. Yeah. Well, I was bouncing off this one. Multiply the second by 3 and add 1. The third one by 3 and add 1.
Yes.
The fourth one by 3 and add 1. You're right. Okay. Or exactly what you said there. Okay. I just pulled the 2 out. So yeah, that looks like a good one. So this is a recursive one. Okay, because it depends on the previous term. So let's see if we can use an n in there. N times 3 plus 1, let's see. No, that won't work. It's a recursive type relationship, okay? Now, we got the pattern. I don't know how to express it as an nth term. I'll go back and look at that. But what you see then, this is a multiplication issue in the numerator. It's a factorial issue in the denominator. Factorials are going in. So the denominator in time is going to get so much bigger than the numerator is going to go to 0. Believe it or not, that's where it's headed. Okay? And the fact that it's alternating makes it even more so. Okay? So let's see how they do. Oh, okay. Sorry. Didn't see this, but it's 3 to the n minus 1. Is that right? No. Yeah, the numerator of this one, not of this, forget this one. The numerator of this is 3 to the n minus 1. 3 to the 1 is 3 minus 1 is 2. 3 squared minus 1 is 8. 3 cubed minus 1 is 26. 3 to the 4th is 81. Yes. Okay. So you're multiplying by 3, but this doesn't actually have that. So forget the 2 here. 3 to the n minus 1. Okay. Let me, in fact, get that 2 out of there. Okay. So there is your pattern. Okay. Now, as n is going to infinity, this wins. Yeah, 3 to n is going big fast, but not as fast as that. And what you have to do is very similar to the last argument. Do several terms here, and this will be 3 times 3 times 3. Okay. Go up to the 3 times 3 times 3 times 3 times 3 over 1 times 2 times 3 times 3, 4 times 5. So after a while, you just need a few more of those. So 3 times 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 3, 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9. Okay? So this is certainly bigger. That is certainly bigger. Those products are bigger. Now you got a 120 down here. That's bigger. But by the time you get here, 3 to the 5th, not sure about there, but by the time you get here for sure, that's 3 times 3 times 3 times 2, so the 2 will be a factor. That one's bigger. By the time you get there, the denominator is definitely bigger than the numerator and keeps getting bigger faster. So yeah, that's going to be, and then the fact it's alternating makes it even more so. Okay? So that will converge, and it will converge to 0. Wow. Some of these patterns are not particularly easy to see, obviously. Okay. Let's see. Oh, they don't do it. Here's Bailey. And here's Corbin. Okay, has anyone else come in since the call roll? All right, good deal. All right, we just did example 8. It wasn't on the, no, it wasn't. It wasn't 8, that was 7. Yeah, we just did example 7. It wasn't on the PowerPoint, so you'll have to pick that up. Okay, not a particularly easy one to see either. And we have Brandon, right?
Yes, sir.
Got 2 Brandons. I want to make sure I got the right one. Okay. Anyone else come in since I called roll? Okay. We just finished example 7 on page 593. Wasn't a particularly easy one either. Okay. So now we're going to talk about monotonic sequences and bounded sequences. Now, do either one of those words mean anything to you? Does anyone know what monotonic means? What does mono usually mean? One. Okay? And basically this means one direction. So a monotonic sequence is one that's either always increasing or always decreasing, going in one direction. Not one like we just had that was alternating plus minus, okay? Monotonic. Bounded sequence means that there's some limit, and after a certain point, everything's going to be within that limit, okay? That means that's a rough idea of bounded. Let's get a little more precise than that. Here's the monotonic sequence. Sequence A sub n is monotonic when its terms are non-decreasing. Okay? In other words, it doesn't mean strictly increasing. It could be constant, but non-decreasing. So the A sub 1 is always less than or equal to A sub 2, is less than or equal to A sub 3, is less than or equal to A sub 4, all the way up A sub n and keep going. Now, they can be equal, but they're not ever less, non-decreasing. Or when it's non-increasing. So A sub 1 is greater than or equal to A sub 2, is greater than or equal to A sub 3, is greater than or equal to A sub 4, and all ends up to A sub n. Can be equal to the previous term, but never less. So monotonic, either it's non-decreasing or non-increasing. Okay? In other words, it's going just in one direction. I said increasing or decreasing. Not quite. It can be the same, but just not decreasing or not increasing. Monotonic, heading in the same direction, or at least temporarily constant, but never going the opposite direction. That's a monotonic sequence. Now, determine, this is example 8, which is the next one. Determine whether each sequence having the given int term is monotonic. Okay? Well, the best way I would say to do this is pick a few terms. What's A sub 1? 3 minus 1, which would be 2. A sub 2 would be 3 plus 1, which would be 4. A sub 3 would be, second? 3 minus 1, which again would be 2. So what you think? Not monotonic in any mean way, shape, or form. Alternating between 2 and 4, 2 and 4, 2 and 4. Ain't gonna happen. Okay? Not monotonic. How about this one? B sub 1 would be 2 over 2 is 1. B sub 2 would be 4 over 3. B sub 3 would be 6 over 4. B sub 4 would be 8 over 5, is that right? Okay. B sub 5 would be 10 over 6. B sub 6 would be 12 over 7. Okay. All right. This is 1, approximately 1.3, 1.5. 1.6, right? Brain's not working now, but what was that? 12 over 7. Someone punch it in the calculator. 1.6 too? 7. Okay. So far it looks like that is increasing. Monotonic, not decreasing. Let me put it that way. Not decreasing, meaning it's not getting any smaller. Okay? And sure enough, that kind of makes sense. You're doubling the numerator, only adding 1 to the denominator. So numerator is going up faster than the denominator is, so it's got to be increasing. Okay? So monotonic, it is. What you think about convergent? Kind of hard to say. In fact, let's not get into it. No. You can't really say it now. Okay? How about C? C1 would be, excuse me, sorry. What? Second? Yeah, so that's 1, so this will be 1, right? C2. 4/3. C3. 9 over what? 7? Okay. C4. 16 over 15? Is that what you said? Okay. C5. 6. Okay. What did you say? 63? All right. Now, monotonic or not? Okay. Certainly increasing here from 1 to 1.3. And I can't say for sure, but I can tell you for certain it's decreasing here and decreasing big time here. So definitely not monotonic, the entire sequence. Now, once you get past some point, you're probably monotonically decreasing. Okay? But with all those in there, you're not. This one, you're monotonically increasing, and that one bouncing back and forth and back and forth. All right, let's see how they did it. Sorry, my eye is beginning to itch like crazy. And this has happened every day this week. It's fine when I leave home in the morning, and the more I'm in here sitting over this, it just gets crazy. Is it turning red? Can y'all tell? It wasn't this morning. I don't know what's going on. I do know I had a treatment on Friday, and that always bombs my immune system, and it seems like conjunctivitis is the easiest thing that it does. And it did it. Okay, the first one, sequence alternates between 2 and 4, just like we found. Definitely not monotonic. Okay? The second one, the sequence is monotonic because each successive term is larger than its predecessor. And there it goes. And we didn't do them all, but you know, it does look like they are steadily increasing. However, I think that looks like it's going to have a limit to it because it's not increasing, it's increasing less each time. So it looks like it could have a limit. We're not doing that yet. Note that because n is positive, you can multiply each side of the inequality by 1 plus n and 2 plus n without reversing the inequality sign. What in the world are they talking about there? I don't see an inequality sign. What are they talking about? Beats me. So, what they said is true, but I just don't see what inequality sign they're talking about. Okay. Oh, this is it, isn't it? Yeah, this is B. So they're saying, is that always less than the previous one? Okay? And what they did to the top one, this is b to the n. B to the n plus 1 would be 2 times n plus 1 of 1 plus n plus 1. The question is this always less than that? And answer is yes, but still don't know the question mark there. So what they did here is multiply the left-hand side. You got two sides of the inequality by okay. What they did was multiply by the product of n plus 1 times n plus 2. Let's see if that's what they said. They didn't say product. They should have said product. If they had, I think that would have been fine. Because you multiply this side by n plus 1 times n plus 2. 1 plus n times 1 plus 2. Then it wipes out the 1 plus n and you get 1 plus 2, or n plus 2 up here. You do it there, and that is your n plus 2. So that wipes out this factor, and you have 2n plus 2 times n plus 1. Because, yeah. All right. Pretty tricky. I'm going to expand on this a little bit, okay? B sub n is equal to 2n over 1 plus n, okay? The next term, the b n plus 1 term, is going to be 2 times n plus 1 over 1 plus n plus 1, okay? Now, the question is this always less than that? Okay? And here's what they're going to do. Multiply this one by n plus 1 times n plus 2. Multiply numerator and denominator. Oh no, you only need to do the numerator, okay? Because that's a positive number and it doesn't change the inequality. Multiply this by n plus 1 times n plus 2. Okay? Well, this n plus 1 wipes out that one, and that's where they get this is, now this isn't b sub n anymore, but now this is 2n times n plus 2, or 2 plus n, it doesn't matter. Okay? This one is, this is n plus 2, so this wipes out that one, and this is 2n plus 2 times n plus 1. Okay? Now, they're saying the inequality sign doesn't change. But that's where they get that term there. Okay, that's exactly how they do that. So I'm going to erase this and see what they say next. Okay. So that is 4n plus 2n squared. Yeah. Is that less than or equal to 2? Okay, when you FOIL this, you get 2 plus 2n plus 2n would be plus 4n plus 2n squared. So obviously this is less than that because this has a 2 added to it. So for any n, it's always going to be 2 more than the previous. Okay? so 0 is less than 2. Always. Starting with the final inequality, which is valid, you can reverse the steps and conclude the original inequality is also valid. Okay. Now, C, this sequence is not monotonic. Let's go back and see what C is. C is that one. Okay. C to n is n squared over 2n minus 1. Okay. The second term is greater than both the first and the third term. Okay. Now, we just looked at a few of them, and after a while you saw it was definite. So the second term was the peak. So that can't be monotonic. If you left off the first term, it would be monotonic, decreasing. But with the first term in there, it's not. Okay. Note that if you drop the first term, the remaining sequence is monotonic. That's what I just said. Okay. Now, that's monotonic sequence. Now let's look at bounded sequences. Okay, here's your definition. Sequence A sub n is bounded above when there's some real number, capital M, such that A sub n, that nth term in there, is always less than or equal to that upper bound, M, for all n. No matter how far you go, you're always going to be, the A sub n, will be less than that. That's bounded from above. In other words, M is the upper bound of that sequence. A sequence A sub n is bounded below when there's some real number n. I'm used to seeing little m here, but they use capital N, such that n is less than or equal for all A sub n. Okay, for all n past A sub n. The number capital N is the lower bound of that sequence. Now, a sequence A sub n is bounded when it is bounded above and bounded below, then you're obviously kind of like you're squeezed in there. Not the squeeze theorem again, but it's sort of the same kind of principle. If you're bounded from above and from below, you're bounded. Now, one important property of the real numbers is they are complete. What do we mean by that? Draw that real number line. There aren't any missing values, okay? Complete. There's always, there's no gap in that at all. No holes, no gaps in the real number line. Set of rational numbers does not have that completeness property. Does anyone know why? Yeah. There are irrational numbers between any two rational numbers, okay? Irrational would be one that cannot be expressed as a ratio of two numbers. So in between, say, any two rational numbers, you can come up with an irrational number that's in between those two. So therefore, the rational number does not be. The completeness axiom for real numbers can be used to conclude that if a sequence has an upper bound, then it must have a least upper bound. That means an upper bound that is less than all the other upper bounds for that sequence. Okay? For example, the least upper bound for this sequence, which is n over n plus 1. Okay? If you started plotting those out, it's 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6, 6 over 7, 7 over 8, n over n plus 1. Okay? The least upper bound has got to be 1. Okay? So every one of those numbers getting closer to 1. No matter how far you go, you're going to get closer to 1, but you're not ever going to reach 1. So its least upper bound is 1. Certainly 2 is an upper bound. No question. 1.1 is an upper bound. But 1 is the least upper bound. Okay? So, theorem 9.5, bounded monotonic sequences. If a sequence A sub n is bounded, that is above and below, and is monotonic, then it has to be convergent. So if it's bounded and it's monotonically increasing, not decreasing, and not decreasing, then if it's bounded from above, it's got to have a limit. And that limit will be, by the way, that bound. Okay? Oh, the least upper bound, sorry. If it's bounded from below and monotonically decreasing, but never can reach there, then the greatest lower bound will be the limit there. It does have a limit. It does converge. All right. Kind of makes sense? All right. Here's example 9. Yeah. Here's a sequence. A sub n is 1 over n. Now the claim is it's both bounded and monotonic. So by 9.5 it must converge. What's it bounded by? From above by 1, okay? From below by 0. And it's monotonic because 1 over n is getting less and less and less and less and less, okay? But it's bounded from above, which doesn't matter, from below by 0, so therefore it does converge, and it converges to its greatest lower bound, which is 0, okay? Now here's a sequence, n squared over n plus 1, okay? Certainly that's monotonic, right? Increasing, 1, or is it monotonic? 1 over 2, yeah, the first one would be 1 over 2, the second one would be 2 over 3, the next one would be 9 over 4, yeah, it's monotonic, increasing every time, but not bounded. Bounded from below, for sure, but it's not bounded from above. Okay. Now, just a little hint here. If you look at the ratio of the leading terms of that fractional form, that comes out to n. N increases without bound, so that's what the ratio increases without bound. Okay? Just something you can fall back on if you need to. All right, here's C. Here's a sequence that is, what would that be? First term. Second term. Third. Fourth. Yeah, it's bouncing back and forth between -1 and 1, -1 and 1, -1 and 1. Bounded from above by 1, bounded from below by -1. But not monotonic, so therefore not converging. Okay? We didn't prove that last one, but certainly not monotonic. Make sense? Is there a D? No, there is no D. Looks like there's room for it. Oh, that finished 9.1. Okay, on the nose. So homework exercises, do any of the odds 5 through 9. All 3 of those are at calcchat.com. Number 9 is at calcview. Do number 11. It's at calcchat also. Do either 13 or 15 or both. They're at calcchat. In fact, I think I would do all 4 of those. What it is matching the sequence with the figure. And excuse me, only 13 and 15 have answers in the back at calcchat, but I think you can do all 3 of those, all 4 of those. Then do either 17 or 19. They're both at calcchat. Do either 21 or 23. They're both at calcchat, but 21's at calcview. Either 25 or 27. They're both at calcchat. Any of the odds 29 to 41. They're all at calcchat, but only 29's at calcview. Okay. I did say 29 to 43. I hope I did anyway. All at calcchat, 29's at calcview. Any of the odds 45 to 51, they're all at Calc Chat. 49 is at Calc View. Any of the odds 53 to 59, they're all at Calc Chat. 53 is at Calc View. And then either 61 or 63, they're both at Calc Chat. And then 65 is a compound interest problem, which I think you might find you've run into before, but if you haven't, you'll probably run into again. Number 67 is an inflation problem, which unfortunately you'll run into sometime during your lifetime as well. And then there's exploring the concepts. You can look at 69 or 71 if you'd like. I don't know if either of those are at Calc Chat. 73 is one you could do. 75 is a proof, so that's up to you whether you want to try it. 77 and 79 are true-false. You can certainly look at those. I think they're at Calc Chat also. There's a nice little sequence here that's a pretty famous sequence. Justin, who's pretty famous, is here too. This is the Fibonacci sequence. Anyone know that one? Huh?
I've heard of it.
Yeah. Okay, let me just give it to you. Since I think, yeah. Here's the Fibonacci sequence. Okay? Pretty famous one. Just have to remember. Yeah. Okay. It's 1, 1, 2, 3, 5, 8, 13, 21. Anyone give me the next term? 34. How'd you get it? Yeah, you add the previous two. Okay. You have to have the first two, 1 and 1. You add those, you get 2. Add those, you get 3. Add those, you get 5. Add those, you get 8. Add those, you get 13. That's the Fibonacci sequence. Fibonacci. Oh, by the way, probably not a bad time to bring this up. This, of course, I think my biggest class, and of course my best class, right? How many research papers do I have? Uno. Yes, 1. Okay. Guess what? Only a few weeks left, folks. Don't put it off till the end. Get your research papers. Get working on those. Okay. By the way, I didn't realize this till I just read it. In the study of the progeny of rabbits, Fibonacci, this is how he came up with this, okay? They multiply like rabbits, okay? And they get, the numbers grow quite big. I had never heard that. But he encountered this sequence that now bears his name. Now, I did hear, I'm pretty sure he's the one, I think was the son of a rich merchant and got to travel all over the world. He loved mathematics, and he observed mathematics in all the different cultures he went to, and he brought things back and put them together, published books. Whether he did anything original, I don't know. I guess he may have. Maybe he came up with this originally. But anyway, it bears his name. Now, has anyone ever heard of the golden ratio? Okay, that's tied to Fibonacci sequence. And I won't do any more of it. It's well worth a read. Has anyone ever heard of the Parthenon? A building in ancient Greece. It's just, and it's ruins now, but still you can see that it was an incredibly great building, okay? And part of the reason is the Greeks knew Fibonacci sequence, and they knew the golden ratio, and they did a lot of their construction and architecture using that ratio. In other words, it's the ratio of the length to the height is a certain thing in lots of things. Da Vinci, I think, used golden ratio in many of his drawings and paintings and a lot of the stuff he did. It's been and in nature it shows up. You know what a cockle shell's, seashell is? That follows the seeds in a sunflower. The spiral there follows Fibonacci sequence, the golden ratio. There are so incredibly many things in nature that follow Fibonacci sequence and golden ratios. It's unbelievable. Something as simple as that. Rabbits propagating, wow, shows up all over the place. Enough of that. Using a sequence 83, I think you can do. Squeeze theorem, another example of that. 85 you can do. 87 and 89 are both proofs. You can do those if you want to. You don't need to. It's up to you. All right, that finishes 9.1. Any questions on 9.1? And let's move on to 9.2. And again, these are the only two sections we're going to cover in Chapter 9. But let's hit this. So what we did in 9.1 was sequences, okay, which is just listing of numbers, terms, What we're doing in 9.2 is then related but not the same. In fact, some places you'll see they're sort of really closely related. But this is a series, not a sequence. But they are connected. Okay? So let's go from current slide. And let's look at infinite series. Let me take a look. We've been going since... this would be, if you needed a decent little break time. Do you need a break? Okay. I kind of could use one myself. So we'll pick up. All right. So like we were saying, section 9.1 was infinite sequences. This is now infinite series. What is an infinite series? Well, 9.2 series and convergence. We'll talk about that as well. We talked about sort of converging of a sequence. There are things that tie it to sequences as well. So, we'll understand objectives here to understand the definition of a convergent infinite series and use the properties of infinite geometric series, which is a pretty handy one. And we'll use the nth-term test for divergence of an infinite series. Notice not for convergence, but for divergence. So what in the world is an infinite series? Okay? One important application of infinite sequences is representing infinite summations. Okay? And there is the key. A sequence is, infinite sequence is any list of numbers. An infinite series is the sum of those infinite list of numbers. Informally, if a sub n is an infinite sequence, then the summation from n equal 1 to infinity of a sub n is a sub 1 plus a sub 2 plus a sub 3 plus, not just listing them, adding them together. Plus a sub n plus ... Keep on going as long as and goes until infinity. That's called an infinite series, or simply a series. A sequence is a list. A series is a sum. Okay? Infinite sum. The numbers, A1, A2, A3, are called the terms in the series. Now, we call them the terms in the sequence as well. But there they were separated by commas. Now they're separated by plus signs. Okay? They are the terms. For some series, it is convenient to begin the index at n equals 0, whereas most of the time with sequences, we begin at n equal 1. Okay? But now we will sometimes use n equals 0. Okay? Or some other integer. -3, 15. You could start these just about anywhere you wanted to, okay? But as a typesetting convention, it is common to represent infinite series as summation of A sub n without specifying where it's beginning. It's the summation of A sub n. Whereas if you put A sub n in braces, that's a sequence. Summation of A sub n, that's a series. Okay? In such cases, the starting value for the index must be taken from the context of the statement. So to find the sum of an infinite series, consider the following sequences. Okay? Now, here is where these two concepts kind of collide, you might say. I was going to say overlap. They actually collide here. Okay? A partial sum would be one term, or the sum of two terms, or the sum of three terms, or the sum of 15 terms, the sum of 85 terms, something like that. Those are called partial sums. So S sub 1 for a sequence A-N, S sub 1 would be A1. S sub 2 would be A1 plus A2. S sub 3 would be the first three terms. S 4 the first four terms. S 5 the next first five terms. S sub n the first n terms. Those are your partial sums. Guess what they form? A sequence. Okay? Now, this sequence may not have a rule like the other sequences did, but this is a sequence, a listing of numbers. Okay? If this sequence of partial sums converges, then the series is said to converge and have the sum indicated by this next definition. So if the sequence of partial sums, that's a sequence, converges, then we say that series also converges. So here's your definition. Definitions of convergent and divergent series. For the infinite series, the summation of n equal 1 to infinity, understanding you could have n equal 0 to infinity, or n equal negative 3 to infinity, or n equal 5 to infinity, whatever. But anyway, that sequence, our series, summation, A sub n, the nth partial sum is S sub n, which is A sub 1 plus A sub 2 to A sub 3, up to A sub n, where n is some finite number. Okay, no longer infinite, some finite number, S sub n. If that sequence of partial sums, when you do a sequence of those, S sub 1, S sub 2, S sub 3, 4, 5, n plus 1, whatever, converges to some value s, then the series, which is that summation, converges. The limit s is called the sum of the series. Okay? So s would then be a1 plus a2 plus a3 plus a4 plus an plus the next, the infinite series. Okay? That would be the sum. If S sub n diverges, that sequence of partial sums diverges, then the series is said to diverge. So in other words, if that sequence doesn't converge on something, that's a sequence of partial sums, then it's a divergent series. All right, well, let's do one. Here is a series. Summation of n equal 1 to infinity of 1 over 2 to the n. When n is equal to 1, it would be 1 over 2 plus, this is a summation now, 1 over 4 plus 1 over 8 plus 1 over 16 plus on and on and on. All right, now, it has the following, I was going to say, the following partial sums, that's just one. It's S of 1 is 1/2. End it right there and you got 1/2. End it there and you got what? 3/4. Anybody? 7/8. 15, 16. And on. You just take half of the distance there. So, does that sequence of partial sums, that's S of 1 is 1/2, S of 2 is 3/4. S of 3 is, as you said, 7/8. S of 4. Oh, it just keeps on going. What you think? Does that sequence of partial sums seem to have a limit? What? 1. Definitely does. Getting closer and closer and closer to 1, but never actually reaching 1. Okay? So, sure enough, therefore the series converges, and it converges to that same value, 1. Okay? Now, I don't know if you noticed this, but that is 2 to the n over 2 to the n minus 1. 1 over 2, 3 over 4, 7 over 8, where the denominator is the third term is 2 to the third, which is 8. Next one would be 2 to the fourth, which is 16. 15, 16, 31, 32nds, 63, 64ths, on like that. Sure enough, it's 2 to the n minus 1. Now, that minus 1 is subtracted from 2 to the n, not 2 to the n minus 1, it's 2 to the n minus 1 over 2 to the n. And that sequence of partial sums does converge to 1. Now, they haven't shown you how to do this yet, but do the ratio of those two. Generally, that's a good, handy way to do it. All right? Because that's true, it follows that the series converges and its sum is 1. Okay? Here's the Bth one, okay? The nth partial sum of this series, okay? Summation of n equal 1 to infinity of 1 over n minus 1 over n plus 1. Okay, let's do a few of those. What would be the first term? 1 minus 1/2. Next term? Okay, 1/2 minus 1/3. The next one? 1/3 minus 1/4. The next one? 1/4 minus 1/5, and so on. Okay? Now, just looking at that, can you tell if that converges or not? Any ideas? Here's something to notice. Here you're subtracting 1/2 and adding 1/2. Subtracting 1/3 and adding 1/3. Subtracting 1/4 and adding 1/4. So it's 1 minus 1 over n. 1 over n plus 1. That, sure enough, is that. Now, is that the only way you can get that? Okay? Well, that's the easiest way anyway, because you see, whatever your first one was, it's minus 1 over n plus 1. The nth partial sum, give me an n. Second? 3? Is that what you said? That would be 1 minus 1/4. So that would be 3/4. Give me a bigger n. 5, okay? 1 minus 1/6, that would be 5/6. So sure enough, that one's going to converge as well. And what will it converge to? 1. Because as n goes to infinity, this thing's going to 0. So it's converging to 1. Okay. So several ways to get around and look at the convergence there. Okay? Because the limit of S sub n is, as n goes to infinity, is 1, because the denominator is going to increasingly huge numbers, then 1 over a huge number is going to be closer and closer to 0. So the series converges and its sum is 1. How about this one? The summation of n equal 1 to infinity of 1. Which is 1 plus 1 plus 1 plus 1 plus 1 plus 1. Okay. Does that if you looked at the sequence 1, 1, 1, 1, 1, 1, 1, 1, 1, that certainly converges, right? Does the series converge? No. No matter how far you go, the next thing is one bigger. And it's never converging to anything. That diverges because S of n is n. As n goes to infinity, that's getting bigger and bigger and bigger. So 1 is 1, 2 is 2, and n is 3 is 3. So S of n is n. That sequence of partial sums diverges. No matter how far you go, the next one's always bigger. No, not bounded. The sequence of partial sums is not bounded. All right. Now that one that we were talking about before is called the telescoping series. Okay? And that's what I was pointing out before. These two add to 0, those two add to 0, those two add to 0. So you just have 1 minus whatever the last one is. 1 over n plus 1. Okay? Same thing here. These two add to 0, those two add to 0, those two add to 0, those two. Okay. Note that the B2 is canceled by the second term, the B3 is canceled by the third, and so on. I don't like to say canceling. They add to 0, which is canceled. All right. Because the nth partial sum of that series is of this series. Is that the same one he was doing before? Yeah, okay, that. Okay. Because the nth partial sum of the series is b sub 1 minus b to the n minus 1, it follows that a telescoping series will converge if and only if that last b sub n approaches a finite number as n approaches infinity. Okay? In other words, b sub n can't get increasingly big. If it does, then it's never going to converge. It has to approach a finite number. Moreover, if the series converges, then its sum, okay, the sum of that as n goes to infinity. And remember, understanding that b is approaching some finite number, then that would be b1, that same b1 from there, minus the limit as n approaches infinity of b n plus 1. So if that limit exists, if there is some number, that's what it's saying here, if it approaches a finite number, that number exists in the series convergence. Make sense? Seems almost like we're running around in a circle, but it's okay. All right. That by the way, there was a little blurb at the bottom of page, or on the inside margin of page 599. The study of infinite series was considered a novelty in the 14th century. There was a logician, a logic specialist, Richard Swiseth, I don't know how to pronounce that, whose nickname was Calculator, solved a certain problem there. Now, I have never run into this name before, so if someone wants to pursue that as a paper topic, that might be pretty interesting. All right. Now, okay, I'm pretty sure we did example 1. Yeah, we did example 1. Okay, yeah, those 3 pieces. Okay, and we did telescoping series. By the way, there's a further information there: 6 ways to sum a series. There's a journal article that might be an interesting paper topic too. You have to go there to get it. Okay. Now, let's do example 2. I was just making sure they didn't show example 2. Okay. All right, let's do it here. I'm trying to get the most white page. Whoops. How did that happen? Okay. Thought I'd already done that. I guess not. I guess this is the first writing we've done here. So example 2 is writing a series in telescoping form. Find the sum of this series, the summation, n equal 1 to infinity, of 2 over 4n squared minus 1. Okay? This is always the best thing to do, but generally it's not a bad idea. Start listing a few terms. What would be your first term? Get me started. Numerator? 2, okay, over. First term would be 3, isn't it? Wait, yeah. 4 times 1 is 4, minus 1 is 3. Plus, because this is a summation, next term, numerator, 2 over 15. Plus 35. Plus, okay, 63. Is that what you said? I'm almost lost myself here. 63. Plus 2 over. Say again? 99. Okay, 99. Okay. Now, all right. I don't see very much that's telescoping there, do you? Okay. Nothing reaches out and smacks me with it. There's nothing that's canceling out as far as I can see. Now, when you have something like this, okay, let's think back to things like your integration using partial fractions. Now, this isn't an integral, but it's a summation, and summations and integrals are sort of related. So you could write this as 2 over, I don't know if this is going to work, but this is something you can try. This is 2n plus 1 times 2n minus 1, isn't it? Okay. Well, let's see if that helps any. Okay. That would be 2 over, when n is equal to 1, that would be 3 times 1 plus 2 over, and I think that would be then 2 would be 5 times 3. I say 5 and write a 2. I don't know where that came in. Is that right? Okay. Plus 2 over 7 times 5. Right? Plus 2 over 9 times 7. See? Plus 2 over 11 times 9. Yeah, that was giving us exactly the same thing. Right? Okay. Well, that didn't clear up anything for me, but it helped me see an easier way to get that, rather than 2n squared minus 1, I just take the next odd number, multiply it by the previous odd number, okay? That works, okay? But if we carried on the same type thing we did with partial fraction, we could say this could represent a over 2n plus 1 plus b over 2n minus 1, right? Okay, and see what that gives us, okay? And we want that to be 2 over 2n plus 1 times 2n minus 1, okay? Now how we went about solving that, I usually did it in the opposite order, so I might flip it around here. Multiply this by 2n plus 1 times 2n minus 1. Multiply this by 2n plus 1 times 2n minus 1. Multiply this by 2n plus 1 times 2n minus 1. Okay, and what does that give? Everything out there goes out. 2n plus 1s go out there, minus 1s go out here. And what we have is that, I'm going to reverse these, 2 is equal to okay, before I do that, I'll go on and do it. A times 2n minus 1 plus b times 2n plus 1. Okay? Now, remember a little trick we did before? We said, let's pick something that makes this go to 0. What would that be? N equals 1/2. Would that make that go to 0? Okay, let n equal 1/2. And then this goes to 0, and 2 is equal to, and 2 times 1/2 is 2 plus 1 is, 1 plus 1 is 2, right? So b is equal to 1. If n is 1/2, this goes to 0, right? And then you have 2 is equal to, and n is 1/2 here, that would be 1 plus 1 is 2. 2 is equal to 2b, so b is equal to 1. Okay? Now, let's do n is equal to negative 1/2, right? N equals negative 1/2, that goes to 0, right? And that would then give you 2 times negative 1/2 be negative 1 minus 1 is negative 2, so a would be minus 1. So a is equal to minus 1. Okay, so this gives us this. I'm going to start with the b. 1 over 2n minus 1 minus 1 over 2n plus 1. Right? This is the same as that, right? So now let's do our series with that. When n is equal to 1, we're doing the summation as n equal, yuck. Where did this go? Here we go. All right. N equal 1 to infinity. Okay? So let's do this. 1 over, when n is equal to 1, what's that first one? Anybody? When n equal 1. Second? What did you say? I said. I know, n equal 1. That's 2 times 1 is 2 minus 1 is 1 minus 1 over. Second? I think it's 3, isn't it? Right? Okay, now let's do n equal 2, right? That was n equal 1. Now do n equal 2. That would be plus 1 over second. Okay, this one. 2 times 2 is 4 minus 1 is 3 minus 1 over, what's that, 5? That's 5. Okay, plus 1 over, when n's equal to 3, 5 minus 1 over 7, right? Plus 1 over 7 minus 1 over 9, right? Keeps on going. Look at here. There's your telescoping. Second? Yeah, okay. And you're going up because it's 1 over that. So, hard to see that from the first. Okay? Sort of hard to, yeah, still impossible to see here. But, thinking of this and treating it like we did partial fraction, come up with A and B that represent that, and there we came up with these things, and sure enough, it's going to telescope down, so it's 1 minus 1 over n. So obviously, actually it's not minus 1 over n, it's minus 1 over 2n plus 1, whatever your maximum n is, but that's going to 1. Okay? Now, I wouldn't have known what that was heading toward, but it is indeed going to 1. Okay. So it would be, the limit would be 1 minus 1 over 2n plus 1. Okay? And as n goes to infinity, that goes to 0. Okay, so it's going to 1. All right. Okay. All right. Now we're ready to hit geometric series. Now, the one thing I had meant to do, I scanned right by it twice. I kept stopping and forgetting to. This example 1, that first one there, they have a clever little illustration in your text, okay, for this one, the partial sums here, okay? This is that partial sum, 1 over 2 to the n, okay? Oh, man. This is heavy. All right. The first one is 1/2. Draw your square. 1/2 of the square is that. And then add to that 1/4. And then add to that 1/8, 1/16. You're taking it halfway, half of what remains every time. I'm running out of things. 1/32, 1/64, and it keeps on going. And sure enough, you're getting closer and closer to the full square, which is 1, but you never reach there. So that's a little graphical illustration of why that is indeed going to 1. All right. Now let's go to geometric series. This is a very special, very useful series, and here's what it is. Summation of n equal 1 to infinity of 1 over 2 to the n. And man, it seems like we've seen that, haven't we? Okay? That would be 1/2 plus 1/4. The one I just had up there. 1/2 plus 1/4 plus 1/8 plus 1/16. That's a geometric series. And here's why it's a geometric series. Okay? It can also be written this way. The summation is n equals 0. Now, it doesn't always have to be, but in this case it is. N equals 0 to infinity. Okay? Of some factor, A. Now, what factor is common to all those terms? What factor is common to every term in there? Anybody? Factor is common to every term in those sequence.
2.
Second?
2.
Okay. The denominator is 2, so the whole thing would be 1/2, right? Okay. So that would be 1/2 times some r to the n. Okay? What would be left over here? You factor out of 1/2. Factor out of 1/2, you'd be 1. Factor out of 1/2 here. 1/2. Factor out of 1/2 here, you'd have a 1/4, and then a 1/3. Yeah, I mean 1/8. You know, and something like this. Well, then you have a multiplier, you might say, that's raised to some power, and that was your 1/2 again. The a was a 1/2, and your r was a 1/2 raised to some power. Okay, so it'd be a plus a times r plus a times r squared plus a times r cubed plus a times, that's what you had here. A times, with n equals 0, that first one would be r to the 0, 1/2 to the 0 would be 1. So 1/2 times 1 is 1/2. 1/2 times, and n is equal to 1, that would be 1/2 times 1/2 is 1/4. And 1/2 times 1/2 squared would be 1/8. So yeah, you've got that right. That's the geometric series. The ratio, that's what we call this, is the ratio r. As long as that r is not equal to 0. Hey, don't ever put an r of 0, because that makes it meaningless. That would always be 0 then. No way around it. So r can't be 0. Okay? So here is our theorem 9.6, convergence of the geometric series. Geometric series with the ratio r diverges whenever that absolute value of r, that ratio, is 1 or greater. Absolute value 1 or greater. That would be -1, 1, 1.2, anything, -1.07, that would diverge anytime the ratio is greater than 1, the absolute value of it. If the ratio r is less than 1, the absolute value of that, then it always converges, and what does it converge to? Voila. This geometric series, some constant times some ratio raised to the nth power, always converges to the constant divided by 1 minus r, whatever that ratio is. Always, okay, if that absolute value of r is less than 1. Can't be equal to 1, has to be less than 1. Okay? That's a pretty simple formula, isn't it? Now the secret will come to trying to figure out what's the ratio, what is the constant, and what's the ratio. If you get that figured out, then it's real easy to come up with the conversion, if that r is, absolute value of r is less than 1. So let's see if they've got one here. This is example 3, and sure enough it's there. So what do we have here? Oh, they did most of the work for you right there, didn't they? Shame on them. Okay. Here's the summation. Let's just do it this way. Summation of, from n equals 0 to infinity, of 3/2 to the n. What's your constant? Three. Okay, that's just there by itself. So that's your constant, 3. And what's your ratio? 1/2. And then every time you do it, 1/2 raised to the nth power. Okay? Because 1 to the nth power is 1, 2 to the nth power is 2. So yeah, that gives us you. There's your constant, there's your ratio. And that ratio is less than 1. So can you write down what that... Okay, answer me. Does that converge or not? Does it converge or not? What's the rule? The absolute value of the ratio is less than 1, then it converges. Okay? Ratio is 1/2. Not the constant. The ratio is 1/2. R to the n. Okay? That's less than 1. It does converge. What does it converge to? Anyone recall? Geometric series. Okay? Go back a thing. Here's what it converges to. The constant over 1 minus r. Okay? So that would be 3 over 1 minus 1/2. And what would that be? Anybody? 6. 3 over 1/2, which is equal to 6. That converges, and it converges to 6. Done. Without having to list a single term, all you have to do is identify your constant, 3, identify your ratio, 1/2, and then use the formula. 3 over 1 minus r. Now, isn't it pretty obvious by this formula that your ratio can't be 1? Okay? If your ratio was 1, you'd be 3 over 1 minus 1 is 0. Can't do it. Okay? Or, if it was, this ratio was anything greater than 1, or absolute value greater than 1, then you would have a negative number here. And how many series add to be negative numbers? None. Okay? So, pretty obvious that has to be 1 or less. Less than 1. Okay. So there is your A. Let's see. Well, let's see. Need to erase it. I was thinking my writing wouldn't be in their way, but it is. Okay. Oh, they listed some of them. Why not? 3 times 1/2 to the 0th power is 1. 1/2 to the 1st power is 1/2. 1/2 to the 2nd power is 1/4. Okay. Start adding those up. Why bother? You don't need to. The ratio here is 1/2. The constant is 3. There it is. So just write down the answer. That would be 3 plus 3.5. 1.5. That would be 4.5 plus 3/4 plus 3/8 plus 3/16 plus 3/32. You could do all that if you wanted to, but why? Just write it down because that ratio is less than 1. It's 1/2, less than 1. Series converges, guaranteed, and it's A, which is 3, divided by 1/2. 1 minus 1/2 is 1/2, and that goes to 6. And here is a figure that shows this. You start adding those up, getting closer and closer to 6, but never, ever getting there. Make sense? Works every time. Let's see, is there a B one here? I think so. Now, here's a geometric series. Summation of n from n equals 0 to infinity of 3/2 raised to the nth power. Okay? Now, the only constant you can see here is 1. Okay? You can't pull anything else out because all that is raised to the nth power. So the constant is 1. What's your ratio? What's your R? Anybody? 3 over 2. Now, what smacks out and hits you about that? It's greater than 1. So guess what you can say? Diverges. It will never, ever converge. Okay? Because this would be 1 plus 3/2 plus 9/4 plus 27/8. Guess what? Every one of these numbers is getting bigger, bigger, and bigger. You keep adding bigger numbers to big numbers, and you're never going to converge anywhere. That is a ratio of 3/2. Therefore, it does not converge. Don't even bother listing the numbers on it. It can't converge. Because the absolute value of R is greater than 1, series diverges, don't even mess with it. Okay. All right. Let's go back and do example 4. I think this will be the best place for it. Let me see if there's a little bit more room. No. I think this is the best place for it. Example 4. And by the way, even though it's not on the slide set, it is at larsoncalculus.com. You can go for an interactive version of this type of example. Maybe not exactly one, but this type. Use a geometric series to write 0.08 as a ratio of two integers. Okay? In other words, write that as a rational number. Okay? Now, are y'all familiar with this notation? The bar over it, what does that represent? Anything the bar covers is a repeating unit. So this would be 0.08080808080808 forever. Okay? And since there's a pattern there, that means this is a rational number. If that had been 0.0800800008000008, not a pattern there. I mean, it looks like there is one, but it's not. That would be an irrational number. Okay? This is a rational number because it is a pattern. Okay? Now it says, come up with a ratio of two integers. Okay? Now you can use that with infinite series, but let me just show you a simple way to do it without using a geometric series. Okay? Because this, I can remember doing this somewhere in junior high or somewhere. I mean, it's not that difficult. Okay? First thing you do is multiply this by 10 to the power with that number of zeros. In other words, repeating unit of 2, so multiply by 100. So let's let x equal this, and then 100x is equal to 8.08 repeating, right? Multiply that by 100 and you get that, right? Okay? Now subtract this one from that one, the top from the bottom. That gives you 99x is equal to, well, guess what? You subtract those, go away, is equal to 8. Divide by 99. And you have x is equal to 8/99. Hey, you can't get much simpler than that. You didn't need to use a geometric series, okay? But you could if you wanted to. So let's see, how would we do that? Anything I can think of would not be, okay. So this would be 0.0808080808 dot dot dot. It just keeps on going. Okay? Now, what you may notice here, this can be written as 8 times 10 to the minus 2 plus 8 times 10 to the minus 4, right? Because this would be this one, right? Add to that 0.0008, that's 8 times 10 to the minus 4, plus 8 times 10 to the minus 6, plus 8 times 10 to the minus 8, and so on and so on and so on, right? Okay? Now, I hope it's pretty obvious to you that would be a series from n equal 0 to infinity of 8 times 1 over 100, right? raised to the nth power. That would be 8 times actually, that would be 1, not 0. Oh, I see what they did. They did 8 over 100 as the first one, and then did it. Sorry. Okay. I was wondering how they wound up with a 0 there. They couldn't have a 0. So here's how they did that. I can't get my eraser to come on. There it comes. Okay. So they did it this way. 8 over 100, which by the way would be 4 over 50, which would be 2 over 25, so you could do any of those numbers, times, and then it would be 1 over 10 to the n, or 2n. Okay? Is that right? So when n is equal to 0, that would be a 1, so that would be 0.08. And then when n is equal to 1, yeah, I think that would work. Okay. Okay. So that would be 1 over n squared. No, 1 over 2 to the n. That would be it. So it's so much harder with this. Summation n equals 0 to infinity of 8. I'm just going to write it 2 over 25. Okay? Yeah. 2 over 25 times 1 over 10 squared to the nth power. That's it. Okay? And that's it. So what's your n, or what's your A is 2/25, and your ratio is 1 minus 100. 1 over 1 minus 100. Okay? That's your R. So this would be 2/25 divided by 99 hundredths, okay, which would be 2/25 times 100 over 99, that would be 4, and that would be 8 over 99, which is just what we got. Why go through the agony of doing all that? Coming up so you can start with n equals 0 and stuff like this. It's so easy just to do it the simple old-fashioned way. But that did show you got the same results. Exactly the same results. Okay? Sorry about that. Okay. Now, it says here, there's a little thing at the bottom of the page here before we get to the other. The convergence of a series is not affected by the removal of a finite number of terms from the beginning of the series. Okay? And let me show you this. They didn't put this on the slide. I don't know why. Let me put this out here for you. The summation of n equal 4 to infinity of 1/2 to the n. Okay? And the summation of n equals 0 to infinity of 1/2 to the n. Okay? They both converge. Okay? And because you know what this one is, this is 1 divided by 1 over 1 minus 1/2. So that would be 2. That converges to 2. All you have to do for this one is to add up the first 3 terms, okay? Or 4 terms, whatever. That would be 1 when n is equal to 0, plus 1/2 when it's equal to 1, plus 1/4 when it's equal to 2, plus 1/8 when it's equal to 3. Add those together, and that gives you goodness gracious, 3/2. Oh man, 3/4, 7/8, 1 7/8. So take this, which was 2, minus 1 7/8, and that would be 1/8. Okay, that would give you the value of the other. So even if this is starting at some bizarre number, not 0, just add up the first 4 of those, 0, 1, 2, and 3, and then subtract that from your one that you know already. Okay. Now, that done, let's look at the properties of these infinite series. Goodness gracious, I'm running out of steam fast here. So, summation of a sub n, that's an infinite series, okay, and summation of b sub n. Let's say both of these are convergent series. Now, let's let capital A, capital B, and little c be real numbers. If, and we said this is a convergent series, if that converges to capital A, and summation b sub n converges to capital B, those are real numbers, whatever they are, huge, small, whatever, if those are that, then the following series also converge, and here are the sums. Okay? So if you have a summation n equal 1, now this time they're not doing n equal 1, so 0, n equal 1 to infinity. Now we're looking at just infinite series. These are not necessarily geometric anymore. We left those already. Okay? These are just convergent series. N equal 1 to infinity, c times a sub n, and you multiply that, pull the c on the outside, and that's c times the summation of n equal 1 to infinity of a sub n, but we know that to be a, so that's c times a. Okay? There's 1. That's the constant multiplier rule. The summation, which will also be a different rule too, is the summation of n equal 1 to infinity of a sub n plus b sub n. Well, without any proof, that's the same as the summation n equal 1 to infinity of a sub n plus the summation of n equal 1 to infinity of b sub n. Well, that's a plus b. And sure enough, that's what it is. Or if that was a minus sign in there rather than a plus, that would be summation of a sub n, which is a, minus the summation of b sub n, which is b, so that's a minus b. Now, I'm going to throw another one out here to you. Okay? If you had the c times this and that same c, then you can factor those out here than here, then that would be c times a plus b or c times a minus b. You could combine all those together. That indicates the infinite series are basically linear in nature. These are the linearity properties or principles. Okay? They don't really call them that, but that's really what they are. All right? Now let's look at the nth term test for divergence. Okay? Pretty exciting stuff, isn't it? Theorem 9.8. The limit of the nth term for a convergent series, okay, if the summation of n equal 1 to infinity of a sub n, if that is a convergent series, okay, then the limit as n approaches infinity of a sub n has to be 0. You can't have this a being anything greater than 0, that nth term. If it's greater than 0 and you keep adding, you're going to get a bigger and bigger sum. It has to, that last term has to go to 0. So, if your sequence of those terms does not go to 0, there's no way that series can converge. No way. Now, just because that nth term goes to 0 doesn't guarantee you have convergence. But if that nth term is not going to 0, there's no way it's going to converge. Okay? Now, the contrapositive of this provides a useful test for divergence. Contrapositive means you're saying the opposite thing in kind of the same way. This is the nth term test for divergence. It states that if the limit of the nth term, this is what I just said, of the series does not converge to 0, the series must diverge. If that was converging to, if that nth term converges to 0.0000000000000001, that's going to converge, diverge. No way. It has to be identically 0 before it even has a chance to converge. Doesn't guarantee it will converge, but it has to. Anything greater than 0 is not going to work. Okay? So, if the limit as n approaches infinity of a sub n is not equal to 0, even if it's a negative number, it doesn't. If it's not equal to 0, then that summation from n equal 1 to infinity is going to always, always, always diverge. Now, again, let me say, just because the limit might be 0, it doesn't guarantee it does converge, but if it converges, that limit has to be 0. Okay. So, let's do example 5. For this series, the summation n equals 0 to infinity of 2 to the n, let's look at the nth term. Okay? The nth term is 2 to the n. And what's the limit as that n is going to infinity? Of 2 to the n. What's the limit? As n is going to infinity, 2 to an infinitely large number is going to be an enormously large number. No way that's ever going to be 0. Okay? So therefore, this is going to be a divergent series beyond a shadow of a doubt. That would just be 1 plus 2 plus 4 plus 8 plus 16 plus 32. That's blowing up incredibly fast. So, of course, that is going to diverge big time. So the limit of the nth term is not 0. The series diverges incredibly fast. Okay? Now, how about this one? The series n factorial over 2n factorial plus 1. Okay? Now, here's a little trick. Divide everything, numerator and denominator, by n factorial. That will leave you a 1 up here. This is 1 over 2 down here, plus infinity down here. Because 1 over n factorial is 1. So that's going to go to 0. So this will be 1 up here and a 2 down here, 1/2. Okay? That's the nth term. The limit of that as it goes to infinity is 1/2. Is that going to converge or diverge? diverge, okay? Even though that's a small number, 1/2, doesn't matter, it's not 0. If that's not 0, it's got to diverge, period, okay? And sure enough, it's a small number, 1/2, but there's no way it's ever going to converge because that's not 0. So that is not 0, it diverges. The first one is going to infinity, that's got to diverge. This one, even though the limit is 1/2, still not 0, so it diverges. Good thing.
A power problem, you got a house out here, and they have you shut down everything. Anything you got, laptop, computer, whatever it is, turn it off and unplug.
Okay, say that one more time.
Unplug all everything that's powered up, your laptop, and it's plugged in the plug.
Right.
Now turn off everything and unplug.
Okay, it can't operate. Okay.
Just told me so. Going around trying to get spread the word. Got several people up down the hall telling everybody.
Okay. All right. Thank you. I guess maybe they're afraid it's going to blow something. I don't know.